All right, so from yesterday, real quick, just wrap up the symmetry stuff, and I want to just look at a couple more examples, and then I I assume it'd be probably nice for you guys to have like a day to work on. Then I can adjust due dates. I mean, if I need to, those are just kind of suggested anyway, but I can postpone those a little bit and adjust those. Um, Symmetry stuff. We were talking yesterday about symmetry of functions, topological symmetry, functional symmetry. And I want to just return to that. We didn't quite finish up. So we've got our tests for symmetry that you need to be aware of. If it fails both tests, what does that mean? If it fails the test for even symmetry and the test for odd symmetry, what's that mean? Doesn't have symmetry, right? No useful symmetry. Okay, so back to the even and odd. Why do you expect that they call even symmetry and odd symmetry odd symmetry? It doesn't really seem to be reflected in visually what you see, what types of symmetries those are. There's nothing really even about that or odd about that necessarily just by looking at it. What do you think? Has to do with the powers, yeah. So it has to do with polynomials because we deal with polynomials so much. If a polynomial only has even powers of the input variable, say x, only has even powers of x for each term, then you don't even have to do the test. It's automatically even symmetry. If a polynomial only has odd powers of x in each term, then it's odd symmetry. If it has a mixture of some terms with even and some terms with odd, it's neither. So for example, like you tell me real quick, this polynomial what kind of symmetry does that have? Odd, right? Because all of the powers of x are odd, right? Okay, how about this one? Okay, what about the constant? How's that even? It is, but how? No. What power of x is that? 0. Yeah. We would never write it that way, but that's the same thing as saying x to the 0, right? Okay, so a constant is an odd power, or an even power, sorry, right? So then that one is even. Okay, and then what's nice about that is when you have rational functions, which is just a ratio of polynomials, you can quickly look at the top and look at the bottom, and you can decide, okay, the polynomial on top is even or odd or neither. Polynomial on bottom is even or odd or neither. And then you can use those fractional rules, and you can really do it quickly, right? Without having to even apply the tests, the functional test. You don't even have to oftentimes do that, right? Does that make sense? Okay. Give me 1 to 5 on that stuff. I got to make sure we're okay on that, all that stuff. Okay. So maybe real quick. So then you tell me, let's just do a couple quick samples of this. What if you had something like this? What kind of symmetry is that going to be? What's it going to be? Yeah, it's odd. Good. How come? What do we get on top? Even on top, right? Bottom is odd. Just like your sine rules, even divided by odd is odd, right? What's even? What are the ratios that are even? Good. Even over even, odd over odd. Okay. Now, what if I change this and I did something like, what if I change that? So maybe I make that an X. Now what's the symmetry? Mm-mm. What is it? Mm-mm. What's wrong with the top? It's a mixture, right? Even and odd means neither, right? Because look here, I've got an even exponent and an odd exponent. So we get none or neither over who cares? Because if it says none anywhere, it's none. There's no symmetry on that one. Okay, so what's the advantage of this? What's the advantage of this symmetry? Well, we know this one's going to be even over even, which is even. Look, we could have made our work a lot simpler, right? How could we have cut our work in half? I'll give you a hint. See what I'm saying? It's just a reflection over that line. Everything on the right side of the table occurs on the left side of the table, right? Look at what I mean. So that gets reflected there. This gets reflected there. Now, what about this part right here? You might be thinking, okay, well, look, that's negative and that's positive. Yeah, it has to be, right? Because if I do a graph of this, what's happening here? We get this vertical asymptote, right? We get this vertical asymptote in the middle. If I were going to do a sketch of this thing, what's it look like? So here's the y-axis. Doesn't it just look like we've got this point at square root of 2 over 4, or square root of 2, 4 is our coordinates to that point, right? So if we go over here, square root of 2, 4, well then the graph is just going to look like that, right? Yeah, right? It just does something like that. What's it going to do on the other side? It's going to be reflected, right? So I don't even really have to do the other side. I can just figure out what the sketch looks like on this side. And on the other side, we're going to get the mirror image of that. And so, yeah, you are going to see, like, whereas the slope in this interval is negative, here it's going to be positive, right? It has to be in order to make the graph symmetrical. But do you need to even really fill out the table on this part? I would say no, you really don't, right? You can just get half the sketch and then reflect it. Okay, you see my point? When we get up to the curve sketching part, I'm jumping the gun a little bit, but I want you to kind of be thinking ahead. Remember, our goal here, I know we're just installing first derivative test, right? That's all we're really doing right now. But eventually, this is just one piece of the puzzle. We're going to draw all this stuff together and really focus on building complete tables and sketching functions. The culmination of this section we're working on is called curve sketching. And at the end, you're going to get some really big assignments that are just going to be, and I'll give you time to work on them, but they're just going to be and it's probably almost the most important thing you do all year, because you just get analyzing functions. So you're actually doing a real analysis. When I say real, I mean like mathematically real number analysis, which is kind of a more advanced topic. But at least you get a little flavor of that, more than you typically. I mean, like I focus on this way more than the textbook does. But this is something you'll use fairly immediately in college when you actually use calculus. Does that make sense? Okay, we good so far in this stuff? Question? I mean, it. Yes and no. Yes and no. It kind of depends. Like, I think I've told you this. I don't really like AP calculus sometimes because I feel like it doesn't emphasize all the right stuff. It just gets you through. In my opinion, it gets you through. I mean, it's good, but it doesn't hit stuff like this hard enough, and it doesn't hit like optimization hard enough, and then it emphasizes some other things that aren't really very important. Like the stuff on simplifying limits that we did earlier in the year. We don't need to spend that much time on that stuff, I think, because it's not. You don't really ever do it. It's not. It's not something. When you apply this in physics or in engineering, you don't really use it very much. So, kind of. I mean, like Andy was telling me, he had some people he knew, some friends he knew that had gotten fives on the BC test, like second year, like second year calculus AP test, and in the class that he's in and they're in, you're theoretically supposed to be able to, you know, at at some colleges you're supposed to be able to skip that class, and they were failing and dropped out. I mean, so it's like the AP test was not, they had done as high as you can get on the AP test, and it wasn't even remotely enough. So I wouldn't bank on it. Like my recommend, I'll talk to each of you individually about this, but when you're picking your classes in college, unless you are very comfortable, I don't think it's a good idea to skip ahead unless you really are comfortable. And I can see that I want to be able to see the syllabus of because it varies from college to college a little bit. Depends if they're on a quarter system or a semester system. It's easier to skip ahead on a quarter system. I skipped two, but Stanford was on quarters, and so it wasn't quite the same as skipping a whole year. It was just two quarters. Um, does that make sense? I mean, I wouldn't have done that. There's no way I would have skipped the whole year. And I don't know that I should have. I mean, it was hard. I don't know that I should have done that necessarily, but Andy skipped a semester, but he didn't skip a whole year. Yeah. And I mean, if you look nationally, the number of kids that don't retake calculus from the beginning, Calc 1 in college, even if they take it in high school, it's like 90 some percent of people just redo Calc 1 in college. Yeah, it's not like it's really common to skip stuff, but that long answer to a short question. But when we get there, I'm happy to kind of talk to you about it when you're picking. This year when you're registering for classes, you're looking ahead at your schedule for next year at the end of the year. Okay. So we just did this. Okay, let's look at another one. Let's look at a trig one. Same kind of thing. Let's just build a table. Let's use the first derivative test and build a table here. So what do we need to do? And they give us a domain. So I can already start that on what's my domain going to look like? 0 to 2 pi. And we're going to have open endpoint at 0, open endpoint at 2 pi. Okay, now what do we need? Yeah, we got to differentiate, don't we? Okay, so let's calculate the derivative. Let me scoot that over just in case we need more room. We might. So derivative of the first term. Chain rule, good. So what's going to be? 2 sine x times cosine x. Good. There's the first link, right? Derivative of hand squared is 2 hand. Now, derivative of hand, in this case, derivative of sine is cosine x plus cosine x. Okay, so we need to find, now what you tell me. You walk me through this. So what do I need to add to my table next? Okay, we're the derivative function, I'm assuming, right? Derivative function equals 0 or undefined, so all the critical numbers. Is our function, our derivative, undefined anywhere? It's not. It's, how do you know? Explain to me how you know. Say it again. It is. It's. You're right. It's composed of only well-behaved functions, and there are no denominators, right? So think about this. If sine is well-behaved, its domain is all reals, and cosine's domain is all reals. The product of the two, there can't be any problems, right? Now, if I were dividing by sine or cosine, of course, then I have to be careful because I have to exclude from the, or I would have from the domain of the derivative, I would have to exclude any zeros of the function on the bottom, right? And then those would be places where the derivative was undefined. But we don't have any of that stuff going on. Okay, give me 1 to 5 on that concept. Does that make sense? Okay, if I have sums or differences or products of well-behaved functions, I inherit no problems. Okay, so nowhere undefined. It does potentially equal 0 in places, though, right? Now, normally when we get up to the next section, I would not, I would continue to differentiate and just create the second derivative vertically and do like side work where I'm finding zeros of the derivative, right? Does that make sense? Because we really, remember, this goes back to some stuff we did previously where we were calculating higher derivatives, second derivatives. I don't know if we really ever did any third derivatives, but second derivatives. And when we were doing implicit differentiation, a lot of times we ended up having to solve for y prime. But when I solved for y prime, sometimes it gave me like a quotient, which is not very convenient to differentiate. So remember I told you, don't mess with that. Just keep going vertically so you can just use product rules and get your y double primes. And then when we need to eventually substitute for y prime, we'll do some side work over here where we'll find out what is y prime so we can substitute. Does that make sense, just what I'm talking about in terms of a procedure? Okay, here, because we're not even calculating a second derivative, we can just do everything vertically if we want to. So if we want to find out where this thing is 0, what are we going to need to probably do to solve that equation, right? So if we set this equal to 0, this is a good thing for us to look at because now we're solving a trig equation, right? We've got an equation involving trig functions. Think how we solve equations in general, right? What we always try to do with polynomials, for example, if we can, is we'd like to use the zero product property, factor and use the zero product property. Well, there are other options if that doesn't work, but that's always a great approach, is if we can factor something in a convenient way and then just apply the zero product property. Can I factor this? What could I do to factor it? I could factor out a cosine. Okay, now this accomplishes something really important. If I factor out a cosine x, then I'm left with 2 sine x plus 1. Okay, what do you think is so great about those factors? What do I like so much about those two factors? Okay, how come? Oh, okay, good. Because they're homogeneous, right? They only have one type of function, right? They're not, that makes sense? We've separated the two different species of trig function here, and it's a lot easier to deal with. Anytime I've got mixed trig functions in a single factor, that's always going to make things a little tougher, right? So we always like to separate the functions, which we did. So if we apply the zero product property, then look what happens. Cosine is equal to 0 where on our domain? That's just a unit circle question, right? So cosine, if we'll go over here, we'll just say, here's my unit circle, right? Cosine, oh man, cosine x equals 0 when x equals what? When it equals pi halves, right? Or 3 halves pi, because cosine is the x coordinate on the unit circle, right? Okay, when x equals pi halves, 3 halves pi. So there's two critical numbers. Okay, what about this? 2 sine x plus 1 equals 0 when sine x equals negative 1/2, right? So what happens when you've got a factor like this that's not just a monomial? If I want to find the zeros of this factor, I got to first of all isolate the trig function, right? So I'm solving for the trig function, and then I'm playing a unit circle game where I'm saying, okay, where's that happen? Where does sine x equal negative 1/2? Sine is the y coordinate, right? So if I were to locate those on my unit circle, wouldn't those be like right there and right there? What angles are those? Okay, right. So it's like this little angle right here is pi over 6, isn't it? Right? Or 30 degrees, right? But we want to think of it in terms of radians. So if that's pi over 6, then what's the whole angle going to be to there? 7/6 pi. It's going to be pi plus another 6 pi, right? So we're going to get when x equals 7/6 pi or 2 pi minus that 1/6, 11/6 pi. Okay, does that make sense? How to think about that? Okay, so there's all of our critical numbers. Let's just put those in order. So we had the smallest one is pi halves. And then we have 3 halves pi right in the middle. And then we've got 7/6 pi. Well, that's pretty close, just a little bigger than pi halves, right? This may not be completely to scale. It doesn't have to be. I want to make sure I leave myself room for a test point there, right? Okay. And then up here, we've got 11/6 pi. Okay, does that make sense? Okay, all looks good to me. Okay. Yes.
Can I ask like a clarification?
Sure. Yeah, absolutely.
So if I have 5x, how do you know it's negative?
How do I know it's there? Okay, because now think about, let's look at for a second, let's look at our unit circle in a little more detail. Did I ever give you guys a unit circle review assignment? Okay, good. Thought I did. Okay, so you can play your little game with your hand to know what the coordinates are. But what are the angles? The important angles are obviously 0 and 90, right? Though we don't really worry about those. Those are pretty simple, right? The coordinates are just made of ones and zeros and negative ones, right? At those places around the unit circle. But we need the interior ones. So we've got this point right here. We've got this point right there. And we've got this point right there. Okay, well, that's 30, 45, 60, right? Okay, so 30 corresponds to pi 6. How do you know? Well, you can always convert from degrees to radians. So I can multiply like a degrees times pi over 180 is going to give me a in radians, right? So 30 over 180 is just 1/6, okay? So we're going to get pi 6. And the coordinates there are going to be, this is going to be the point, right? So I'm going to get square root of 3 over 2, square root of 1 over 2, which is just 1 over 2, right? Does that make sense? Okay. So if those are the coordinates of that point, then this one right here, which is the one we're looking at, must be same x coordinate, negative y coordinate, right? Because this is positive, positive. Quadrant 4 would be positive x, negative y, right? And quadrant 3 would be negative, negative, but the same numbers. Okay, does that make sense? How we get those values then? So if this is pi 6, then this one right here must be 2 pi backing up by pi 6. Okay? Does that make sense? And this one here must be pi plus an additional pi 6 to get down to that y coordinate of negative 1/2. Oh, the hand trick, right? So the hand trick is it's quadrant 1, and you've got each of your fingers corresponds to one of those 5 special points, right? On the x-axis, on the y-axis, 45 degrees, 30 degrees, 60 degrees, right? Okay, and so all you have to do is, like, if I'm going to pick this point here, I fold that finger in, and then the number of fingers to the left of the point, that's going to give you the x coordinate. It's always the square root of the number of fingers divided by 2. So the square root of 4 divided by 2 is 2 over 2, which is 1, right? The x coordinate is 1. To the right of that is 0. Square root of 0 is 0, right? So 0 over 2 is 0. So I get the coordinates 1, 0. Here, I would get square root of 3 over 2, comma, square root of 1 over 2. Square root of 1 is 1, right? Here we would get square root of 2 over 2, square root of 2 over 2. Here I would get square root of 1 over 2, which is 1/2, square root of 3 over 2, right? And here I would get 0, square root of 4 over 2, so the y coordinate would be 1. Right? You get that? Okay.
It gives you like the 9 trick. I always love the 9 trick.
Yeah. So Andy told me, like, he would see people, like, when he was doing math, he'd see people doing that trick. So you're not the only, I mean, like, every day other people know that trick too. It gets, what's that?
Is this like new to you? You just now figured that out?
No, I've taught it for years. Yeah. And I guess somebody must have showed that to me. I'm sure somebody showed that to me at some point, but I just don't remember when that was. Okay, so what do we know about the table here then? What else can I fill in? I got those critical numbers, so what else do I know? Y prime is equal to 0. Yeah. Okay, so y prime is equal to 0 at all those places. So those are places where I know that we're going to have horizontal tangents to the curve, right? We just need to know what's going on there. So this is where we'd have to apply the first derivative test. So how are we going to figure out what's going on at pi halves? We're using the first derivative test. How do I apply the first derivative test? Yeah, I got to pick test points, right? I'm picking test points that bracket that one critical number. So that means I have to pick a value between 0 and pi halves. That's easy to do, right? Like, we could just pick pi fourths, for example. This is a little tougher. I got to pick one between pi halves and, yeah.
Are those lines constants?
Those are just the horizontal tangents. Yeah, we'll still draw. We don't know though if they're going to be maxima or minima or inflection points. We don't know that yet. That's what we need the first derivative test to figure out, right? So we need a value between pi halves and 7/6 pi. So, I mean, we could pick a specific value if we want to. Like we could pick, oh yeah, what am I saying? Pi halves. Oh yeah, it is. Yeah, I've got this totally messed up. You're right. Yeah, it's not that small. Yeah. So I should move. Okay, so this is really out of place, isn't it? That really should probably be clear down here, and this should be clear up here. You get that? Right? Yeah, we got lots of room in between. So we can move this guy. Let's do that. Let's scoot him over a little bit. Just so it looks right on the first one. I mean, so it's sort of symmetrical. So it's sort of proportional, I guess I should say. So this one's going to be pi halves. Okay, now we can pick our test points. So we can use pi fourths, probably easy, right? I could use pi third, or sorry, I could use pi thirds or pi six or something too, but pi halves is pretty easy. Or pi fourths is pretty easy, right? It's right at the 45 degrees. Here, what would be a convenient one to use here? Pi. Why not just use pi? How about in here? What's an interior point? You get that I have to use, when I'm picking my test points, like it would do me no good to pick one over here to test this guy, right? It has to be the test points have to be in between all of the critical numbers. They also, I don't have any vertical asymptotes here, but if I had a vertical asymptote at like 5/4 pi, I would need to pick something between the vertical asymptote and my critical number. Does that make sense? Okay. We haven't really dealt with a lot of vertical asymptotes yet, but we will get a lot more practice with that. And I've got more to say about vertical asymptotes when we get there. Okay, how are we doing so far on this? Everybody understanding what the first derivative test does? Right? Okay, so what would be a good, I mean, there's a bunch of them, just pick one. 5/4 pi would probably be a good one, yeah. And then how about in here? 7/4 probably be good, right? Would be one between 3/2 pi and 11/6 pi. And you can just kind of think visually on the unit circle. That would just be that point right there, right? Okay, now what about this one? This is kind of a weird, this is the one I knew there was going to be something like this on this example. What about this one? 11/6 pi and 2 pi. It's hard to pick a point there because we don't have any convenient unit circle points. So what I would do is I would just use the endpoint. Even though it's an open endpoint, so what? Right? We could still use the value 2 pi, whatever value it's approaching there would be fine. This is not a critical number, so it's not like I absolutely have to pick a value in between these two. Does that make sense? Okay. It's just not convenient to pick a value like, I mean, what else would you pick? I guess you'd have to do something like 23/12. I mean, I don't know what we could reason out what the sign of the derivative would be there if we really thought hard about it, but it'd be a lot easier just to use 2 pi. And if you want to, just call it 2 pi minus, right? Just think of it as we're approaching from the left side, from values less than that, okay? So now let's evaluate the derivative function at those places. When I'm evaluating the derivative, I want to use the factored form of the derivative, right? Because then I can it's pretty hard to know if I'm plugging in, like for example, pi fourths into the purple function up there. that's going to be hard to know if the overall value of the derivative is positive or negative because I'm adding up these two terms, right? How do I know if this term is bigger or smaller than that term if they're opposite signs, right? You see my point? We might as well look at the factored form where I can more easily tell what the sign of each factor is and then just use sign rules. Make sense? Okay, so this is the one we're going to use right here. F prime of x equals the factored form. Okay, and now we can evaluate each one of these pretty easily. So let's try we'll evaluate the first test point, f prime of pi fourths. Well, what's that going to give us? The cosine of pi fourths is positive or negative? Positive, right? Okay, how about the second one here? What's the sine of pi fourths? Positive or negative? Positive. So 2 times a positive plus 1 is positive, right? Positive factor times positive factor is positive. There you go. So we know. See how I'm doing that? Okay, how about pi? Okay, so cosine of pi is positive or negative? Negative. Okay, sine of pi is, what's the value of sine pi? 0. So 2 times 0 plus 1 is positive, right? So the overall sine of the derivative at pi is what? Negative. Okay. Okay, because, whoops, missed that, didn't I? Okay, so because we're going from positive to negative at a horizontal tangent, what does the first derivative test tell us? It's going to be a maximum, isn't it? Right? If I'm going from increasing to decreasing, it looks like that. Okay? Give me 1 to 5 on that. Does that make sense? How we got all that? Okay. All right. How about now we can knock this guy out. Pi or 5/4 pi. What's going on at 5/4 pi? So we got to come back over here. F prime of 5/4 pi. So that's quadrant 3, right? Okay, in quadrant 3, cosine is negative. Okay, sine of 5/4 pi. Negative square root of 2 over 2, right? Agreed? Okay, times 2 is just negative square root of 2. Negative square root of 2 plus 1 is overall is what? Square root of 2 has got to be bigger than 1, doesn't it? See what I'm saying? So I've got a negative number bigger than 1 plus 1 makes it still negative, right? So I'm getting negative times negative, which is positive. Okay, so then what kind of animal are we dealing with there? I'm going from decreasing to increasing a horizontal tangent. So we've got smooth minimum, right? Okay, and then finally 7/4 pi. 7/4 pi is in quadrant 4, right? Where sine is negative, cosine is positive, right? Okay, so we're going to get positive, and then the sine of 7/4 pi is the same as the sine of 5/4 pi. Negative square root of 2 over 2, right? So I know I'm going to get negative there just like I did there. Okay, you see how useful it is to know the unit circle well? I mean, how it really pays off. It makes this so much easier. So we get negative, which means that this must be a maximum, right? Okay, and then we know the increasing and decreasing intervals just from the signs of the derivatives between the critical numbers, right? Okay, good. Well, we made it through almost a problem today.